Welcome and thank you for joining us today. There are several registrants still signing in, so I'll pause for just a moment or two to allow everyone to get settled. Thank you for your patience. Excellent. Hello, and thank you for joining today's broadcast on probabilistic data structures and how they allow you to cheat the storage requirements and computational load of many common data tasks. Our presenters today are Kyle Davis, Head of Developer Advocacy, and Loris Crow, Developer Advocacy Manager here at Redis Labs. Today's webinar is being recorded, and all attendees are in listen-only mode. We'll take questions at the end of the webinar, and at any time during the broadcast, please feel free to enter your questions using the chat module in the communication panel. Following today's webinar, we'll send out an email with a link to the recording for future viewing or sharing with colleagues. With that, Kyle, I'd like to turn it over to you and Loris.
Hey, Robin, thanks for that. Today, we're going to be talking about one of my favorite subjects, probabilistic data structures. I know that might sound a little bit weird, but it is really one of my favorite things to research, and it's really one of the more interesting things that you can find in the data structures. Today we're going to go through a little bit about Redis itself, and then we'll get into probabilistic data structures and a few different ones. So first, I just want to give you a little introduction to Redis. We call this the database for the instant experience. And basically, you start looking at what people want. Human perception is less than 100 milliseconds or so. And so to do that, when you talk about end-to-end round trips and all that stuff, your application's latency, you really need to respond to things in a really, really small amount of time. So sub-millisecond response times. And that leaves you with the requirement for a very, very fast database. In that case, Redis is a great solution for it. So in that, roots are in open source. Redis is BSD licensed. It is open source. You can download it. You can look at the code, all the great stuff about open source. But it's an in-memory database. It's made for a variety of use cases, high-performance operational, analytical, and hybrid methods. If you take a look at this, Redis, you may have heard of it. It's very popular. Let's take a look at a few numbers here. First thing, we have been pulled on Docker Hub more than 1 billion with a B times. This is as of last month. We're at 1.17 billion pulls. Now, we know that that's not a billion people using it, but it's more like pipelines and people building things automatically that contribute to this number. But it does still underlie the popularity and widespread adoption of Redis. When we look at how people love us, it's literally true. In 2017 and 2018, the numbers aren't out for this year yet because it just started, but we are the most loved database. And that's the people who wanted to continue to develop with us or are looking to develop with us. And this is from Stack Overflow. It's a great honor for us, and we see it, and people love using Redis. It's a great thing to talk about because people all love hearing about it. The story about Redis is there's 3 main things that we kind of talk about. We talk about performance, we talk about simplicity, and we talk about extensibility. So performance, let's look at that in more detail. So on the left side here, we have a summation of a benchmark done by Avalon Consulting Group, a third-party independent group. The line chart on the left is the latency, in this case. And then you can see we provide lower latency than all the others on the list. And then the bar chart is the throughput. And so we provide more throughput. So lower latency and more throughput. That's a pretty good combination. So I actually am really interested in the one on the right. This is one of my favorite benchmarks. This was done by Google. And they said, how many servers does it take to get to 1 million writes per second? And writes are difficult for a lot of databases. Redis, we handle it pretty well because we're an in-memory database. We read and write it at practically the same speed. So in this case, if you take a look at it, we required 2 servers. Now it says times 25. So Couchbase, for example, here required 50. 2 servers to get to 1 million writes per second. And if you do the numbers here for the annualized cost, that's not insignificant infrastructure. But you're still achieving that with less servers, and in the comparison values with other database systems, you can see that it's quite a bargain. And in fact, it's funny. We knew some people who ran the benchmarks of the other companies, and at least one of those people joined us after they ran that benchmark. So it's a pretty powerful thing to say. With that, the simplicity of Redis is based on data structures. We descend from the key value store branch of the database family. And so what that means is everything in Redis is at some point associated with a key. And then the other side of that key is not just a blob, but a series of rich data structures. Today we'll be talking about some of these, specifically bitmaps, bitfields, and HyperLogLog. But there's other ones too. These are things that you may be familiar with from your CS courses, lists, which are linked lists, hashes, which are hash maps, so on and so forth. So this really provides a useful way of accessing data. If we go ahead and look at extensibility, this is something we'll go into in detail here, but extensibility is a way that you can take Redis and you can do multiple different things with it. Redis started out with a set number of data structures, and those set number of data structures did some things very well, but they didn't do everything. And so the modules interface was developed to prevent scope creep in the core of Redis, but provide and enable people to write their own modules that provide data structures and commands that are first class with everything else. And this really turns Redis from being a relatively simple structure store or key value store into a multi-model database. We have modules that turn Redis into a full text search engine, into a great graph database. There's all sorts of use cases. You can store JSON, but today we'll talk about one in particular, which we'll get to in a moment. And so I can't talk about Redis without talking about Redis Enterprise. At Redis Labs, we also produce Redis Enterprise, which is a commercial enterprise-grade version of Redis. And so it becomes an in-memory multi-model database with all the features that Enterprise provides. But it's great for the large companies that use Redis or smaller companies who use a lot of Redis. In those cases, you're going to want the high performance, you're going to want the multi-tenancy, the high availability, all these features that become a requirement at a scale that open source can do, but maybe requires a lot of footwork to do those. And we think Enterprise is a great way for those large organizations or the high demanding Redis users to really take advantage of it. So now into the meat and potatoes of the particular presentation today. Probabilistic data structures. Probabilistic is a very long word. I get it. Sometimes we call it P11C internally because it is so hard to say for some people, and it's just so long to write. But let's take a look at what they are, because I think this is something that's maybe a little intimidating to people, but it's really quite simple in concept. You have 2 different families of data structures. You have deterministic and probabilistic data structures. Deterministic are what you're familiar with. You put data into a deterministic data structure and you get it out. The structure size is greater than or equal to the data size. This makes sense. There's some overhead, so you have to have that. And then you have some examples of these. These will be familiar from your CS 101 classes. Hash maps. Look at these dates here, by the way. They'll be important later. Linked lists, heaps. These are all pretty normal things that you will see throughout. Now, there's more of these, but this is just some examples I wanted to show you. These were all done in the 50s and 60s. That's a long time ago. That's ancient history in computing. Probabilistic data structures, on the other hand, are a little bit different. The data you put in may be the data you get out. And a lot of times what you're getting is information about the data that you put into it. For example, membership in a set, cardinality. These sort of information is where probabilistic really shines, and this is the sort of information that we can store in a really efficient manner. the efficiency can be shown in its size. This is a really crazy thing. I like to call it the TARDIS of data structures. It literally is smaller than the data you put into it in most cases. So it can be, it's like the TARDIS, the TARDIS is bigger on the inside than it is on the outside. It provides kind of a fuzzy view of the data. You might be able to tell something about something, but you won't be able to tell what's actually in it. And that's important to know. You might be able to say, yeah, what's put into it, membership or the number, the cardinality. So it does this kind of fuzzy view of the data. Some examples you would see is Bloom filters. This is kind of the grandfather of all probabilistic data structures. It was initially conceived in 1970 and then kind of expanded in the 90s. Count-min sketch, HyperLogLog, and Cuckoo filters. We're going to talk about all of them with the exception of count-min sketch today. You can take a look at that on your own. There's more as well. It's really an active part of computer science research. So why would you do this, right? Sometimes speed is more important than the correctness of what you're pulling out of it. So we talk about performance all the time, and we talk about speed. In this case, this can provide you an advantage. Compactness is more important than correctness. Again, we're an in-memory database. We understand that RAM is expensive. So that means that you can have a lot more advantage, and both these may go into together, speed and compactness. And you can keep it all in memory without having to worry about, having giant clusters of servers that have so much RAM. And then you can look at, sometimes you only need having specific guarantees about the data. Maybe you only need to have, for example, presence, not necessarily, exact return on something. And finally, you can use it as a complementary structure. Sometimes it's used in ways that it's used hand in hand. So you both have the deterministic and the probabilistic storage here. And you can do a few extra things by not having to touch that deterministic structure. So before we go any further, we have to talk about one key concept, which is the hashing function. The hashing function is incredibly important to these, and we'll get into exactly how that works a little bit later. But the hashing function, to understand what they do, basically you input anything of any length, and then you get out a very large number, and that's usually written as hex. You can see this, but it's just a number, right? It's very, very large. The properties here that, if you change one part of the input, then the output will be entirely different. So consequently, it's practically impossible to reverse this computationally. And then, we have a couple different families of the hashing functions. Cryptographic hashing, you might be familiar with the SHA-1 or SHA family of cryptographic hashing. There's RIPE-MD, there's a few others as well. And they're different than what we're talking about today. They're very hard to compute, intentionally so. And then they have a very low collision rate. So if you're storing passwords or you're trying to use cryptography, these are very important attributes of a hashing function. But today we'll be using non-cryptographic hashing functions: CRC, murmur, spooky hash, spooky, XXhash, FND, etc. These are very easy to compute, so they're the entire opposite of cryptographic hashing, because you want to compute them very fast. So they're intentionally the opposite. They'd be really bad at storing passwords. And a low collision rate. So the collision rate is not critical. So mathematically, they can be quite different than the cryptographic hashing functions, but they do the same thing, and they're in the same mathematical family. So now that we know this, let's go into the first type that we want to talk about today, which is the Bloom filter. Filter is such a weird term for it to me. Excuse me. But think of it as storage that does some very limited things. So how it works is the items are hashed, and the hashed items are stored in a bit field. I know that sounds a little bit weird, but if you think about bits, right? If you have a number that is a series of bits, ones and zeros, if you keep on overlaying them, this is kind of starting to be how Bloom filters work. They can answer either maybe it has been put into the Bloom filter or definitely not. So this is where the kind of fuzzy view comes in. Maybe. That's not something you're used to in a lot of programming. But the items here, you put them in and you query the status. So you can put something in, and then it is effectively stored in kind of quotes. And then you could say, does it exist? In the simplest form, it never fills up. It just gets worse the more items you put into it. So you specify a size at the beginning, and then it fills. Now, in the more useful form, or the more developed form, it fills to a predetermined error rate, and then it grows. What do I mean by growing? What I mean by growing is that you take multiple Bloom filters and you stack them on top of each other. So instead of it just getting bad as you add items into it, what happens is we keep track of the amount of items added to it. And once it reaches a certain predefined error rate, which we can calculate based on the number of bits in it. Then we add another Bloom filter on top of it. What we want to check, we check those Bloom filters in sequence. So if it exists in any of them, then it is is considered to be maybe. So let's do a quick little demo. This is not necessarily a demo that you would that is representing Redis. This is just an example of how Bloom filters work. So this is an example. I'll post a link to this. This is somebody created this. It's really great though, and it's a very simple, the simplest Bloom filter ever. So I'm going to add a few items to it. I'll add my name, Kyle. So you can see that that went through and added the 0th and the 5th bit. My last name. I'm going to add a couple more bits. I'll add my co-presenter, Loris, his first name, and then Crow. Okay. So now if I go down here and check for or test for the element, or I type Crow, it says maybe. It is maybe in there. Davis is maybe in there, but if you DA is, but DAV is definitely not, because what's happened is they're checking those bits on cryptographic hashing. So in this case, 13 and 8, which you can see here, one of these is not set, so we know for sure that it's never been in there. So we type Redis, for example. That was definitely not something we put into it, but it's still saying maybe. So this illustrates the kind of probabilistic nature of things. So, and here's this. We'll be sending out, we can get you the slides here as well. So this is how you can take a look at this yourself. And I will say this is not precisely how Redis does this, or most Bloom filters do it, but it's a good visual representation. How are Bloom filters used? One of the great ways is username search. So an example, let's say you have a site and you somebody's signing up and you want to see if this username is taken. You can ask a Bloom filter. So you have a Bloom filter of all of the items or all the usernames. And then instead of going through and actually trying to find that in some sort of index, you can just first look at a Bloom filter. And what's great about that is the guarantees here. It doesn't necessarily, if there's a maybe here, it's not a big deal, but you've protected from two people having the same username. We can do that with the data guarantees provided by Bloom filters. Fraud mitigation. Humans don't tend to do things the same way every time. So if you have a series of actions that you're putting into something, and you can kind of measure those actions, you can then put those into a Bloom filter. And if that happens multiple times, it's going to be unusual. So you can kind of do some more checks on top of that. The one-hit wonder problem in caching. A lot of times when you're looking at things, for example, caching a web page, a lot of things are only hit once, and there's no need to cache something that was hit once. So you run it through a Bloom filter, and then when it starts returning maybe, then you say, yeah, I need to store this somewhere else and provide caching for it. Looking at if a URL is malicious. So imagine you have a list of millions of URLs, right, that are considered malicious. You can check this before maybe you make contact with that URL. Looking at transaction privacy, and this is used I think in blockchain. What it does is it kind of goes in, and if you're querying a specific area, that might actually be telling, or your privacy might be revealed if you're looking at this one thing. So you don't want to do that. So instead, you basically have a Bloom filter that you send to somebody, and then you check versus that Bloom filter. So really cool use case. A little bit different than how Redis uses it, but really cool use case. And then rate limiting. In this case, you're going to try to see if somebody has, in a certain window of time, come into something and maybe not let them in again. So if they're saying no, then let them in. If the Bloom filter is saying maybe, then you say, okay, you can't come in for right now, and then you expire out that in a few seconds afterwards. And then content freshness. So this is one of my favorite examples. Let's say that you're going to a website and you always want to send your users, the users of that website, the new articles or something like that, something that they've never seen before, so they continue to consume information or content. You can, every time they read something, you add it to a Bloom filter, and then when you're trying to generate the list of maybe suggested articles, you would then check and see if they've seen all those and provide only the ones they haven't seen before. So it can be a really cool way of doing that. So in Redis, how does this work? It's provided by the ReadBloom module, which is a module that you can download and add to Redis. It has a couple different options. Command to add is bf add. The first argument is a filter name, and then any item that you want to add to it. And then bf exists, and this will check for it as well. So you have your first is your key or your filter name, and then the item that you want to check for it. And we'll say yes, that says maybe or no, effectively. There's other things too, some administration commands that you really only need those two other ones, those two ones previous. So that's Bloom filters. That's kind of the foundational aspect of Bloom filters. But I do want to go into talking about one that's used very often as well in Redis. Is HyperLogLog. It's a really funny name, but what it does is it estimates the cardinality of unique items. So if we take a look at this, it's part of the sketch family of data types. I mentioned count, min, sketch earlier. We're not going to go over that today. There is a module for it, but take a look at it and see. Basically, these all just kind of estimate cardinality in different ways. It's based on bit flipping and counting. So you're flipping bits in a bit field and you're using some counts. I'll go a little further detail into how the algorithm works itself, but you don't really have to know that because HyperLogLog is abstracted by Redis, so you can use it out of the box. It's just some simple commands. Those commands relate to 3 operations: add, counter, merge. Merge can be really useful in ways that you might not expect. The cool thing about it is, no matter how many items you are trying to count, it never takes more than 12 kilobytes of memory in Redis. Pretty amazing. And we'll get into maybe what happens there. There is a standard error rate of 0.081%. So keep that in mind. It will always have that error rate present. How does HyperLogLog work? This is a little bit difficult. So first thing you do, items are hashed. Then you look for the run of zeros and where the first one counts. Then you can go and increment a table cell internally. You count the multiple times with different buckets, and then you find the maximum, and that'll give you your estimation of counts. Now, I will tell you that this sounds crazy, and I feel like I'm a crazy person explaining it because it is pretty complex. But thankfully, like I said, you don't really have to do much with it. How is it used? So Facebook, if you're trying to think about Facebook likes, they don't necessarily use Redis, but this is an example of how HyperLogLog can be used. Let's say you want to see how many unique people have clicked on something and liked something. You don't want somebody to like something twice, right? But you do want to increment that little value saying that 10,000 people like this or whatever. In this case, you can add it to a HyperLogLog. User ID 123 liked this post. Now, if you say it again, user ID liked this post, it won't actually increase the number. So kind of cool stuff can happen there. And you only need the guarantees of getting that cardinality. It may not be important, especially in rendering out maybe that little widget to know exactly who did. You just need to find out how many. You can look at unique reads, and this is kind of a similar use case, but if you're a site like maybe Reddit or something, you wanted to see how many people have done this to maybe calculate out which are the trending articles. This is a great way of doing it. Network attack mitigation. In this case, you're trying to see if you're getting a certain window of unique users in, and if you have all the users coming from maybe like one IP address range, well, that might represent something that is a network attack, and you might do some other things to it. It might be something where you're checking versus something else again afterwards. But anytime you get that maybe, that's when you would want to, or that you have your past a certain threshold, excuse me, then that's when you would want to do maybe some more checking as a complementary method with others. And then this is, I think, one of the most fascinating use cases of it. I did talk about merge being really useful. Advertising providers use this very often. So let's say you have a list of user or person identities that all drive SUVs, right? And then on the other hand, you have a list of soccer moms, and they all have these user IDs. And you want to see if there's much overlap between these two groups. So you don't actually need to know who in those two groups are common. You just need to know a number. So maybe you could serve an ad as an example. So with HyperLogLog, you could merge two values together, and you would then get a number out of it because it won't double count. So it won't say, when you're looking at the numbers, it will actually give you a unique set between the two of them. So it's really cool. You can do some actually really interesting things with that. And then you can look at how we do this in Redis, right? The cool thing about this, there's no module needed. It's built into Redis, and it's been there for quite a few versions back. So odds are, if you've got Redis running, you have HyperLogLog. You just probably never used it. The command to add something is pfadd. It was named after the computer scientist who actually pioneered the algorithm. His name was Philippe Flauget. He's French. I love his name. The first thing in pfadd is the key. And this will be just how you identify your HyperLogLog, and then you add your element after that. And then pfcount, and that will tell you, how many are in that key. So if you have added with pfadd, let's say 10,000 times with 8,000 are unique, pfcount would tell you that. And then pfmerge, you have your destination key as your first, and then you have any number of source keys that you want look at. So really simple to use. You don't have to worry about that algorithm that makes you seem like a crazy person. So I want to go in now and just do a quick demo. This is something I wrote actually a couple years back. I want you to pay attention to a couple of the graphs at the top of the screen. If you take a look at this, I'm going to add some random data in each time I click this random button. And you'll see here, the dark blue represents the HyperLog log, and then the light gray represents the set. So I'm comparing the set versus a set estimating cardinality versus the HyperLog log here. So at this point, when you've added one item, HyperLog log is larger by a few bytes. But let's keep on adding some more items. We start to see it plateau out on HyperLog log. You can see here that it's not going up as much. As we keep on going, it keeps on getting, it only grows very modestly, and that's just overhead. But the set is growing up linearly, and you see you keep on adding to it. Now, if I was to click long enough, and this is publicly available if you want to take a look at this demo, it's easy to download. You take a look at this number will come and show difference at some point. It's all based on the difference between the HyperLog log and there we go. So 45. So we're seeing a small miscount here on HyperLog log. And that's the probabilistic data structure nature. But you can see instead of 835 bytes, we're taking 147. So really cool stuff. Going back to the presentation here. At this point, I'm going to hand it over to my friend Loris, who is going to talk about cuckoo filters.
Yep. Thank you, Kyle. Okay, so cuckoo filters are my favorite data structure, and they have this funny name because they take inspiration from these animals, cuckoo birds, who like to place their eggs into other birds' nests. And yeah, they're not very friendly, but it's a very interesting thing that they do, and it's also an interesting thing that the data structure does. So if we can move to the next slide, we can start discussing the properties of cuckoo filters. So they're an alternative to Bloom filters, so they answer the same question. You have a set, you place items in your set, and when you get a new item, you can ask to a cuckoo filter the same way you could ask to a Bloom filter, is this new item one that is part of my set or not? Have I seen it before or not? Again, you don't get precise answers. The no answer is always correct, but the positive answer is always a maybe. You don't know for certain. Although the error probability is always very slow, same as Bloom filters. With cuckoo filters, you can also delete items, and that's something interesting that you cannot do with Bloom filters. Internally, they work in a completely different way, and that's the reason why you can delete items. And they basically store single bytes from the original items that you insert in, and they shuffle them around as the filter gets filled. And this is why they take up the name. They're named after the cuckoo bird. Let's move to the next slide, please. Thank you. So cuckoo versus Bloom. Why would you prefer one to the other? Well, cuckoo filters are very, very good. They're actually better than Bloom, and they are also more recent to Bloom. If you remember, Bloom filters were from the 90s, while cuckoo filter have been invented and first presented in 2014. They are very, very fast in both lookup because of memory lookup properties, inserting, and even more efficient than Bloom filters. But they have a downside too. They are much more sensitive to misuse than Bloom filters. For example, both filters need to be sized appropriately according to the amount of items that you expect that you're going to put in. But Bloom filters can degrade, as Kyle was saying, or grow, while cuckoo filters and don't just degrade the quality of their answers, but they also become slower and slower and become far slower than Bloom filters. There's also another thing where, let's say that you have a failure in your system and you're not sure if one insert was performed correctly or not. In Bloom filters, you can replay the same insert multiple times and nothing will change. While in cuckoo filters, you will be adding multiple copies of the same item, and that might be not what you want. Another thing is that deletion is an amazing action, an amazing thing that you can do with cuckoo filters. But if you delete an item that you never placed in the first place, you might break the filter because you could potentially delete an item whose fingerprint is colliding with the item that you are deleting. So you have to be careful with that. So when would you want to use Cuckoo? Well, if you know your use case very well, so you know how to size it properly and you know how to use it precisely, avoiding the other two problems that I mentioned in the previous point, then you're perfectly well off. And if you have to delete items because your set might lose some of its members, for example, if it's username, maybe you can have users delete their account, for example, so free up the username or similar things, then we really want to use Cuckoo filters because there are some alternatives, but they are nowhere near as good as Cuckoo are. The commands are basically the same as Bloom filter. They can really be used as an in-place replacement in case you might want to try them out in an application where you're already using Bloom filters, but you have one extra command, and that is the cf.del command, which deletes an item. Cuckoo filters can be found in rebloom as an alternative implementation of Bloom filters, so in the same module that Kyle presented before. That's pretty much it. Thank you, Kyle.
Thanks. Thanks, Loris. Now, that's coming to the end of our presentation. I'm not sure we are currently at time, so I'm not sure we're going to have any questions. We'll try to get back to you on those questions if you do have them. So there's that. I do want to leave some time, though, for Robin to tell us one more thing about our next webinar.
Excellent. Thank you, Kyle and Loris. Before we go, I would like to invite you all to attend our next webinar, which is next week, where Kyle will speak about intelligent session storage and how to drive intelligently personalized experiences with Redis. Visit redislabs.com/resources/webinars to register. Thank you all for attending.